Today we're going to look at section 2.8, graphing linear and absolute value inequalities. Our objectives are to graph a linear inequality and to graph an absolute value inequality. So we need to consider two things when graphing our inequalities, and we're now in two variables as opposed to one variable. So now when we graph, we're going to be on the coordinate plane, not a number line. So we're not just going to have open circles and closed circles, but we're going to have our solid lines and dashed lines. Our solid line is similar to having a closed circle on our graph. But now, when we graph and connect our points, it's going to be solid. When we had an open circle on our one variable graph, now we're going to draw dashed lines to represent it. We also need to have shading. Before, when we shaded a number line, we either shaded left or right. Now we're kind of going to shade either above or below. The only time we don't have an above or below is when we have something vertical, and then we have left or right. So we're going to be picking points, which we call a test point, and then we're going to choose. So for example, if I have a linear inequality here, I don't know if I'm going to shade below the line or above the line. We'll never shade both, one or the other. So what's this test point? Well, hopefully you've seen this in algebra. Let me give you an example. Y is less than, say, 2x plus 3. This is a linear, this is a line, inequality. So if I was to actually graph this, how would I know which side of our line to shade? Well, we use something called a test point. We find a point that's either on one side or the other, doesn't matter which side, and we usually like to use the test point 0, 0 when possible, because it makes our algebra the easiest. If our graph goes through the origin, goes through 0, 0, we have to pick a point other than this, but otherwise, always use 0, 0. It's the easiest. So what we're going to do is test to see if this makes the statement true or false. So I'm going to substitute a 0 in for y, a 0 in for x, and then evaluate each side. 0 is less than 3. Now this is a false statement, which means wherever 0, 0 is, I'm not going to shade that side. I'm going to shade the opposite side. If this was a true statement, I would shade the side that had 0, 0. Let's go through some examples. Our first one is linear, and it's not in any one of our three forms. It's not in slope-intercept form, standard form, or point slope. So what I'm going to do first is put it in the slope-intercept form to make it easier to graph. I'm going to divide both sides by a positive 3 to get negative 2/3 x minus 3. Okay? So now what I'm going to do is graph this. I'm going to go down 3 for my y-intercept. I'm going to go down 2, right 3 for my slope. I'm going to continue this all the way across my graph to get a more accurate graph. Okay. So now I need to decide, is this going to be a solid line or a dashed line? Now, what I need to do is look at my inequality. Well, this would have been a closed circle if I graphed, which means it's going to be a solid line, because we can actually equal the values on this line. Okay? We don't just have to be greater than them, we can also equal them. So how do I know which side to shade? Well, I want all the values that are greater than this line, which you would kind of think of as being up here, but how do we know for sure that these are the points that are greater than the line negative 2/3 x minus 3? Well, we'll pick a test point. And if I look at 0, 0, it happens to not fall on this line. It's actually on one of the sides. So what I'm going to use the test point 0, 0. So anywhere I see a y, I'm going to substitute in a 0. Anywhere I see an x, substitute in a 0. I'm going to get 0 is greater than or equal to negative 3. This is a true statement. So because this is true, I'm going to shade the side that has 0, 0 on it. Now this shading would go on forever, just like this line, but all we're going to shade is the part of the graph we can see, just to get the idea. Let's look at another line. This one happens to be in standard form, so what I'm going to do is find the x-intercept and the y-intercept, just like we had done in this section for graphing lines. Our x-intercept, the great thing about that is y is always 0. Again, remember, no matter what kind of equation or inequality we're dealing with, x-intercept always has a y value of 0. So if I substitute 0 in for y, I'm going to be left with 8x equals 16. Now the reason I was able to change it from an inequality to an equation is because I'm actually solving for the x-intercept, so we actually want to know what x actually equals. So if I solve this, I get x equals 2. Now let's find the y-intercept. I'm going to get that by substituting 0 in for my x value, which if I substitute in a 0, I get 8 times 0, which is 0. So I'm going to get negative, don't forget the negative, negative 2y equals 16. So y equals a negative 8. Now I'm going to plot those 2 points, 2, 0 for my x-axis, negative 8 on my y, 0, negative 8. Now, I'd like more points to make this more accurate. So let me figure out my slope for my line. I went up 8, right 2. So that's a slope of 8 over 2, or 4 over 1. 4 over 1, 4 over 1, and I can continue that all the way through. So now I need to know, is this a solid line or a dashed line? Well, if I looked at this symbol, this would have been an open circle. So that means I'm going to get a dashed line. And I like to just kind of connect every other point sometimes to really make it look dashed. But now I need to pick a test point and figure out what side I'm going to shade. 0, 0 happens to be on one of the sides, so I'm going to go to my original equation. Anywhere I see an x, substituting a 0, and the same thing for y. 0 minus 0 is 0. Is that greater than 16? No, this is a false statement, which means 0, 0 is not a solution to this inequality. So I'm not going to shade this side, which says 0, 0 is a solution. I'm going to shade this side. Because again, this shading, what this shows are all the points that make this statement true. So if I pick any point in the shaded region and substitute it in, this is going to give me a true statement. If I pick any point on this side, or even any point that falls on the line, it's going to make this statement false. And that's, whenever you have an inequality, we have multiple answers, and this is how we show it. Let's do one more line. X plus 7 is less than 4. That's a little bit different than the other ones. So let me try to get x by itself by subtracting 7. X is less than negative 3. If you remember from our section, I believe 2.3 on graphing lines, equations of lines, x equals any number gives us what we call a vertical line. Because we want to find all the points on a line that have an x value of negative 3. Well, those would stack up vertically. So I'm going to go to negative 3 and draw a vertical line. Should this be solid or dashed? Well, this would be an open circle, so I'm going to draw a dashed line. Now, the reason I wrote, when we had that first slide about shading above or below, there is really no above or below. There's a left or right for this one. But you can use a test point still if you're unsure of what values are less than negative 3, which values would work in our solution. So let me pick the test point 0, 0. I substitute 0 in for x. There is no y, so I don't have to worry about it. 0 is less than negative 3. Again, this is a false statement, which means anything on this side is not a solution. So I'm going to shade the left side. And this should make sense. Isn't on the left of this line all the places where x is less than negative 3? Over here, all the x's are greater than negative 3. So let's move on to absolute values. We just did this in our last lesson. Let's see if we can kind of go through and graph these. This is actually in my standard form. A, B is an imaginary 1. Well, it's imaginary. It's there, but we can't see it. And then we have our C value is 2, and our D value is a negative 4. So this is going to be a downward facing absolute value graph. Our vertex is going to be the opposite of this, so negative 2, comma, and whatever this number is, negative 4. Our slope, remember one side of our absolute value, or one ray, is positive, one has a negative slope. We take the A value times our B value, which would be 1/3. So let me go through and graph this. If you had trouble following this, go back and watch the 2.7 lesson on how to graph absolute values. So when I go through this, I'm going to go to negative 2, negative 4, about that point. And then this races down, so that means I'm going to go down 1, left and right 3. So down 1, right 3, and then again I'm going to continue this all the way through. And remember, even though I'm stopping at the edge of my graph, these points do go on forever, and we show that by putting an arrow on our graph. This would be an open circle, so then I would have a dashed absolute value graph. We do test points the same way we do them for linear equations, or inequalities. I'm going to test 0, 0. So this is why it was really important in one of our earlier sections to be able to evaluate and use our order of operations. So 0 is less than negative 1/3 times the absolute value of 2 minus 4. The absolute value of 2 is 2, so we're going to get negative 2/3 minus 4, which 0 is less than, well, this is just negative 4 2/3, just to make it easy for me. Now, you could have stopped here and said, well, 0, is that ever less than a negative number? No. Or you can go all the way down and realize this is a false statement. So I'm not going to shade the side that has 0, 0. I'm not going to shade above my V. I'm actually going to shade below or inside the V. Okay. Again, all of these points, any point that is shaded, if I substitute it in for x and y as a point, will give me a true statement. Let's look at this one. Okay. Again, this is going to be now an upward-facing absolute value. If I factor out my 2, I'm left with x minus 4, which means my vertex is at positive 4, comma, negative 6. You do the opposite of the x and do the same number that's out here, the d value. My slope for my two sides are going to be plus or minus. If I take the a value times the b value, I get 4 or 4 over 1. Because my absolute value faces up, I'm going to go up 4 and left or right 1 for my vertex. So let's go to 4, negative 6. Up 4, right 1, up 4, right 1, and so on. And the same going left. Okay. This would have been a closed circle, so I'm going to graph a solid absolute value equation. Okay. Luckily, my test point 0, 0 works out, so I'm going to substitute in 0 for x and 0 for y. So 0 is greater than or equal to 2 times the absolute value of 2 times 0 minus 8 minus 6. So 0. Again, this is 2 times the absolute value of negative 8 minus 6. Absolute value, to remind you, just is asking how far away from 0 is this number. Well, negative 8 is 8 away from 0. So 2 times 8 is 16. So 16 minus 6 is 10. Is this a true statement? Is 0 greater than or equal to 10? Nope, this one happens to be false as well. It's not always false, it just depends on how the numbers work out. But I'm not going to shade 0, 0, so I'm not going to shade outside the V. I'm going to shade inside the V. And let's try our last one. Okay, this one looks a little bit different because we have this 1 on the same side as the y. So to put in the standard form that we're used to, I'm going to subtract 1 from both sides. Okay. Now to make it easier, I'm actually just going to factor this right away to put it in our standard form. If I factor out a negative 4, that's the same as doing the operation of division. So this is going to make it a negative 9/4. So this is going to be an upward-facing absolute value. My vertex is going to be at a positive 9/4, comma, negative 1. Now to make this easier to graph, I might actually just graph 2.25, comma, negative 1. And my slope is going to be a plus or minus a times b. So 1/2 times 4 is 2, or 2 over 1. Because this faces up, I'm going to go up 2 and then left or right 1 from my vertex. So 2.25 is just a little bit past 2, and then down 1. Okay, so none of my points are actually going to fall on the grid lines now. It should be just a little bit to the right. So what I have here is I'm going to go up 2, right 1, and just a little bit past, up 2, right 1. Okay. And then I can do the same on the left. So if I'm at 2.25 and I subtract 1, I'm at 1.25. So again, I'm just going to be a little bit off of my grid lines. Okay. This would have been an open circle, so I'm going to graph a dashed line. So just make sure you can tell that it's dashed, and then connect from there. Okay, again, I'm going to use 0, 0 as my test point. So 0, you can substitute into the original one if you want. Doesn't matter which, since all of these inequalities should technically be equivalent. And then 0 for my y and x. So this is 1 is greater than 1/2 times the absolute value of 9. Well, is 1 greater than 4.5? Again, it doesn't have to have 0 as one side. That's still a false statement. So I'm not going to shade the 0, 0 side. I'm going to shade the side that's inside the V. So that's how you would graph inequalities, whether they're linear or absolute value. So what if I just don't even ask about the graph? I just ask you to determine if it's a solution. Remember, the solution would be in the shaded part of our graph, but that doesn't mean you actually have to go through the work of shading. If you substitute in this test point, or the point they're asking for, and pretend like it's a test point, it'll let you know if it's a solution. If you get a true statement, the answer is yes, it is a solution. If you get a false statement, then the answer is no, it is not a solution. So I'm just going to do the first one for you, and I'll leave the last two for practice. So here's my inequality, negative x minus y is less than or equal to negative 10. And the first one I want you to try is negative 3, negative 9, a solution. So what that means is put it in as a test point. And I kind of do a little shell to make it easier for me. All I'm going to do is anywhere I see an x, substitute a negative 3. Anywhere I see a y, substitute a negative 9. I get a lot of double negatives here, so I'm going to get 3 plus 9. Is that less or equal to negative 10? Okay, we get 12 is less than or equal to negative 10. Okay, is that true? Nope, this is a false statement. So to actually answer this question, I would write not a solution. Okay. I'm going to leave these two for you to try as well, substituting them in. What if it's an absolute value? Okay. You're going to do the same thing. Let me move down. I'm going to do the negative 1, 7, since we've done a lot with 0, 0. So what if I put a negative 1 in for now x, so be careful, and then put a 7 in for y. So just make sure you put it in the correct order. So a 7, is that greater than or equal to negative 4/5 times the absolute value? Negative times a negative is a positive. So I'm going to get 1/2 plus 3, or 3.5. I'll just write 3.5 and make it a little bit easier. Plus 6. Okay, so now if I think about this, I'm going to have 7 is greater than, okay, negative 4/5 times 3.5 is going to be, if I type this into my calculator, just to make it a little bit easier, is negative 2.8 plus 6. So is 7 greater than, and if I take 2.8 and I subtract it from 6, I'm going to get 3.2, a positive 3.2. So is 7 greater than 3.2? Yes, this is a true statement. So this negative 1, 7 is a solution. Okay, and I'll leave the other two for you to practice. The last thing we're going to look at is, well, what if I actually give you a crazy-looking graph? How could you go backwards and actually write down what each inequality is? So I actually put 3 on the same graph, because that's going to kind of make it a system. We'll talk more about systems later. But if I want to graph all of these together, I'm going to just look at, say, this one first. I'll do this line second and this one third. Because I could, instead of giving you one by itself like I did in all the previous examples, I could ask you to graph multiple ones on the same graph. So let's think what that would look like. So the first one, and any time we put a whole bunch of things together, we like to use a bracket to show they are together. It's kind of when we did our piecewise. We had all the separate parts, so we used a little bracket to show they were all put together. So if I look at this is a horizontal line, and if you remember from 2.3, a horizontal line is always y equals a number. But it's not going to be an equation now since we have shading, but what is this value? 5. Now, this is a solid line, so I know I'm going to have that equal to part. Now, did I shade above the line for greater than, or below the line for less than? And when you have a graph already drawn, looking at the shading is much easier to do it that way. We're going to shade below the line, so it's going to be less than or equal to 5. If I go to line number 2, this is set up really nicely in y equals mx plus b form, or slope-intercept form. So I know my b value, my y-intercept, is 1, and my slope is up to right 3, up to right 3. So I know I have y up to right 3, so slope x plus my y-intercept. Now it's a dashed line, so I know I'm not going to have a little line here for equal to, but if I look here, am I shading above the line or below the line? Well, I'm shading above, so that means I want all the values that are greater than this line. This technique does work too, instead of using a test point, as long as you have the y isolated. If the y is isolated, it makes it a little bit tougher to do this. Our last one is an absolute value. So we know our form is y. So if I look at this, my vertex is right here at negative 5, 1. So I'm going to write this down here, negative 5, 1. Okay, I know this face is up, so I can see that. And my slope is up 1, 2, 3, 4 over 1. So my slope, one side is positive, one side is negative, up 4 over 1. So again, if you don't remember how to go backwards to write this inequality, you can look at the section in the lesson on graphing absolute value inequalities, or just graphing absolute value equations. So what I'm going to do is y. I'm going to take my slope and use that as, remember my slope is a times b, so I'm going to make the a 4 and the b 1. There's lots of different answers for this, but this is the easiest way to do it. Okay. If my b is 1, and now I know this is my c value and my d value. So I'm going to do 1x, and then minus a negative 5 would become plus 5, and then I have plus 1. Now, if you're not sure if this is right, go backwards. My vertex would be negative 5, 1. My slope would be up 4 over 1, and it does face up because that's positive, so you can always go back and double check. If I look at this absolute value, it's dashed, so I'm not going to have an equal sign. And let's see, did I shade above it or below? Well, if I put my pen on any point, I have to move my hand down to get to the shaded area, so it's going to be less than. So this is one thing, and I just put 3 together, how you would write the inequality if I give you the graph.